picture yourself walking toward a wall. First step, half the distance. Next step, half of what's left, then half of that. You keep closing the gap. But in this thought experiment, you never actually touch the wall. Here's the question calculus asks. Even if you never touch it, can you still say exactly what you're walking toward? The answer is yes. And that what you're walking toward is called a limit. By the end of this video, you'll be able to calculate one in under 10 seconds, and know exactly when you can't. A limit describes what a function's output is heading toward as the input gets closer and closer to some value, regardless of what happens exactly at that value. We write it like this: the limit as x approaches a of f of x equals L. Translation: as x sneaks up on a, f of x sneaks up on L. Notice what this does not say. It doesn't say f of a equals L. It doesn't even require the function to exist at a. Limits are about the neighborhood around a point, not the point itself. That distinction trips up more students than anything else in this topic, so keep it in your back pocket. We'll come back to it. The most intuitive way to estimate a limit is brute force. Plug in numbers that get closer and closer to the target value, and watch where the output trends. Let's try. The limit as x approaches 2 of x squared minus 4 over x minus 2. If you plug in x equals 2 directly, you get 0 over 0, undefined. That's not the end of the story, it just means direct substitution failed this time. Instead, try a number close to 2, like 2.1, that works out to 4.1. Now try something even closer, 2.01, that comes out to about 4.01. See the pattern? As x creeps toward 2, the output creeps toward 4. That's the limit, even though the function itself is undefined exactly at x equals 2. This numerical sneak-up method is great for building intuition and checking your work, but it's slow and imprecise for a test. So let's talk about the fast way. For most functions, polynomials especially, the limit is just the function value. Plug in and go. Example, the limit as x approaches 5 of x squared plus 2x minus 4. Plug in 5, 25 plus 10 minus 4 equals 31. Done, no tricks needed. Whenever direct substitution gives you a real number, you're finished. That number is the limit. The only time you need another strategy is when direct substitution gives you the dreaded 0 over 0. That's called an indeterminate form. It doesn't mean the limit doesn't exist. It means you don't know yet, and you need to dig further. Let's revisit our first example properly. The limit as x approaches 2 of x squared minus 4 over x minus 2. Direct substitution gives 0 over 0. Time for algebra. Notice the numerator is a difference of squares. X squared minus 4 factors into x plus 2 times x minus 2. So the expression becomes x plus 2 times x minus 2 all over x minus 2. The x minus 2 terms cancel, legally, because we're only ever looking at x values near 2, never exactly at 2. What's left, the limit, as x approaches 2, of x plus 2, which is 2 plus 2, equals 4. Same answer we got by brute force plugging in numbers. That's not a coincidence. It's proof the algebra works. Try this one yourself. The limit as x approaches 3 of x cubed minus 27 over x minus 3. This is a difference of cubes. The formula is a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. Factoring the top gives x minus 3 times x squared plus 3x plus 9. Cancel the x minus 3, then substitute x equals 3 into what remains. 9 plus 9 plus 9 equals 27. This factoring doesn't always work, especially when a square root is involved. That's when you multiply top and bottom by the conjugate, the same expression with the sign flipped. Example, the limit, as x approaches 9, of the square root of x minus 3 over x minus 9, multiply top and bottom by the square root of x plus 3. The numerator becomes x minus 9. The denominator becomes x minus 9 times the square root of x plus 3. Cancel the x minus 9. The limit, as x approaches 9, of 1 over the square root of x plus 3 equals 1 over 3 plus 3, which is 1/6. The conjugate trick works because it turns a square root subtraction into a difference of squares, which almost always produces a factor that cancels the 0 in the denominator. Not every limit needs algebra. Sometimes you just need to read a picture. The rule: to find the limit as x approaches a of f of x from a graph, trace the curve as it approaches x equals a from the left, then trace it again approaching from the right. If both sides arrive at the same height, that height is the limit. If they arrive at different heights, the limit does not exist. This is where one-sided limits come in. The limit as x approaches a from the left means approaching from the left. The limit as x approaches a from the right means approaching from the left. The limit as x approaches a from the right means approaching from the right. Three important patterns to recognize on sight. A removable discontinuity, or hole. Both sides approach the same y value, but there's an open circle there. The limit exists even though the function might be undefined or defined somewhere else at that exact point. A jump discontinuity. The left and right sides approach different heights. The limit does not exist even though the function may have a value defined right at that x. A vertical asymptote, one or both sides shoot off toward positive or negative infinity. Also results in does not exist. Infinity isn't a number, so the function isn't settling anywhere. And here's the detail that trips people up. The function's actual value at x equals a, shown by a solid dot on the graph, can be completely different from the limit. As x approaches a, the limit cares about the journey, not the destination. Try these before the answer appears on screen. First, the limit as x approaches 4 of x squared minus 5x plus 4 over x minus 4. Factor x minus 4 times x minus 1 over x minus 4. The answer is 3. Second, the limit as x approaches 0 of 2 minus the square root of x plus 4 all over x. Use the conjugate trick. The answer is negative 1/4. Third, from a graph with a jump at x equals 1, where the left side is 2 and the right side is 5, the limit does not exist. So let's recap. A limit is what a function approaches, not necessarily what it equals. Always try direct substitution first. If you get 0 over 0, factor and cancel or multiply by the conjugate if there's a square root. Graphically, check the left and right side separately. They must match for the limit to exist. In the next video, we'll take limits to their logical extreme. What happens as x approaches infinity itself? We'll figure out how to spot horizontal asymptotes in seconds. No graphing calculator required.